Okay, so let's begin. So chapter 2 is about limits and continuity, but the difference here is that limits are going to involve infinity. You've kind of already seen it, but this is just a little bit more. So before we go into it, we do have to remember some things about asymptotes because we are going to be dealing with a lot more rational functions. So if you remember, how do you find an asymptote? You set the denominator equal to 0 and then solve, and that's how you find the asymptotes. Now the actual definition of asymptotes that involve limits basically says the line x equals a of a graph for function y equals f of x is the VA if the limit as x approaches a from the left and the right. I should probably put the plus and the minus here. So from the left and the right is equal to plus or minus infinity, depending on the function that we have. Now the horizontal asymptote, the definition is the line y equals b. Remember, it's horizontal, so it's on the y-axis of a graph for the function y equals f of x if either the limit as x approaches positive or negative infinity. So keep in mind, this is not left and right if it's written on here. It's going towards negative infinity. So going towards negative infinity or going towards positive infinity of the function is equal to b. Now we have an oblique asymptote, aka the slant asymptote, if the horizontal asymptote does not exist, right? And we have this if the limit as x approaches positive or negative infinity of f of x minus ax plus b is equal to 0, then the line y equals ax plus b is the oblique asymptote. And all of these definitions make definitely more sense when you actually utilize them in a problem. Okay, so moving on. In this example, we want to graph 1 over x squared minus 9, and then we want to find the following limits. Okay, so before I do that, I want to graph that function. So let's remember, 1 over x squared minus 9 is a rational function, which means I need to figure out my vertical asymptotes and my horizontal asymptotes. What are they? X cannot be what, and y cannot be what. Okay. Now to find the vertical asymptote, I need to factor the denominator, so that ends up being 1 over x minus 3 and x plus 3 when we factor this out. So x cannot be 3 and x cannot be negative 3. So that's where my vertical asymptotes are. They are at x equals 3, so 1, 2, 3. There's 1, and 1, 2, 3 at negative 3. So I have 2 vertical asymptotes right there. Now my horizontal asymptote, remember Bobo bottom eats DC, so the degree is bigger on the bottom, so y cannot be 0. Okay, or the horizontal asymptote is at y equals 0. So I'm going to draw that right down 0. And then to figure out where the branches are, just plug in some points. And since the horizontal asymptote is right at 0, it makes it easy. You just basically, if it's positive, it's up here. If it's negative, it's down here. So I'm going to plug in a few points. If you plug in, let's say, -5, so -5 squared is 25. 25 minus 9 is positive 14, so 1 over 14 is going to be positive. So that means this branch is right there. The middle guy is going to be a parabola, okay? And the question is, does it go through the horizontal asymptote? So I'm actually going to pick a point here and a point here. So if I pick -1, plug that in, -1 squared is 1 minus 9, that's going to be negative. Okay? At 0, it's also going to be negative. And at 1, it's also going to be negative. So what that tells me is that the center is just a parabola that hugs the asymptotes and just underneath the horizontal. And then if this end behavior is going down, that means the next end behavior is starting up here because the degree is bigger on the bottom. Okay? So there's my graph. Now I can actually find my limits using my graph. So as x approaches positive infinity, where is the function going? Okay, so where is the function going? So as x approaches positive infinity, f of x is getting closer and closer to 0. As x approaches negative infinity, again, the function is getting closer and closer to 0. The next one says, as the limit approaches 3 from the right, what is happening to f of x? So here's 3. If we're approaching it from the right, that means we're coming this way. What is happening to the function? It's going to positive infinity. Now, I'm going to go to this one. As it approaches 3, though, from the left, okay? So I'm going to skip over these asymptotes because I actually want to get to 3. What is happening to this function? So I'm approaching 3. I mean, it's up here, and then it keeps on going over here, and then I approach 3 from the left. Where is this graph going? To negative infinity. So because these two are not equal, that means, does the limit approaching 3, does it exist? No. Alright, I'm going to check on the other side. So here, as we approach -3 from the right, that means I want to go this way from the right, and I'm going to -3. At -3, what's happening to my graph? It is going to negative infinity. But as I approach -3 from the left, where am I going? Up to positive infinity. So again, because these two do not equal, then this does not exist. Okay. Special cases of rational functions when you have f of x over g of x. So two functions above each other. Remember the trick to finding the end behavior of rational functions. We'll actually talk about this in class tomorrow. Alright, let's do some examples. We want to find the end behavior limits of the following functions, which means I basically want to know where is this going in the left and the right direction. So as the limit approaches positive or negative infinity, where is this graph going? Now, when you're identifying the end behavior, basically the leading term, okay, is what dominates. This dominates. So this tells us that this graph is going to be a quartic graph. The others just tell us what's happening in between that quartic graph. But right now we know that this is a quartic. And if you remember, quartics are similar to parabolas except stuff is going on in between. Okay? So it's either going to be up or down. Because this is positive, I know it's going to be up. So my question is, as the limit of x approaches negative infinity, where does this graph go? And honestly, I don't even care about these parts right here when I'm just looking at end behavior, because that is what determines how the graph looks like. So I'm just going to focus on 3x to the fourth. So if I plug in negative infinity here, what do you notice happens? Negative infinity to the fourth, because of the degree is 4, that ends up becoming positive infinity, and positive infinity times 3 is just positive infinity. And the same thing is happening as x approaches positive infinity. So the limit as x approaches plus or minus infinity is infinity. Now this is not a right or left, okay? This is approaching negative infinity. Going this way, it's going up, and going this way, it's going up. Okay, this is the end behaviors. This is not a left and right. All right, so moving on to the next one. Again, this is a rational function. So really what's determining what this graph looks like is the dominating terms. So I'm only going to focus on this. The plus 3 and the minus 1 don't really do anything to my graph. And we'll talk about this when we do the homework in class. So I'm only going to focus on 4x squared over 2x squared. And right off the bat, what do you notice happens? That becomes a 1 because they divide into each other. So we're left with 4 over 2. And then that is the 2. So really, the limit as x approaches infinity from left and right of 2 is 2. And that's it. Alright, next. What is the limit as x approaches positive or negative infinity of 1 over x to the n? It doesn't matter if I plug in positive or negative infinity. What happens to this number, x raised to infinity, is going to be a very large positive or a very large negative. And 1 divided by an extremely large number is going to be 1 over infinity, or 1 over negative infinity is just going to be approaching 0. Okay? Now for this one, looking at them individually, I can't really determine which one is the dominating. Okay? So what we're going to use is we're going to use the subtraction property. So I'm going to split these two up, and I'm going to find the limit as x approaches infinity for pi minus the limit as x approaches positive or negative infinity for 2 over x. And basically the limit of this is just pi, because the limit of any constant is just the constant, minus the limit of 2 over a really big number is just 0. And that equals pi. And that's my limit. That's my end behavior. That means that this function, if I graph it, it should approach pi as we're going to both positive or negative infinity. And we can work that out tomorrow. All right. So you can see now it's kind of getting a little bit more complicated. I shouldn't say complicated, but it's just a little bit different. Okay. So we're going to start off with this next one. And you know what? Let's do this one together in class because there's a little bit more to this than meets the eye. Okay, so let's come back to this one. So before I do anything with this, I can do one of two things. Either I can split it up using the product property, or I can just combine it and make it into a polynomial over a polynomial. So I'm going to decide to combine it. So first off, I know that this right here, to get a common denominator, it's going to be 2 over x plus 1 times x over x. So I can get a common denominator. And nothing is changing here. So this is 5x squared minus 1 over 7x squared. Alright, and now this becomes 2 plus x over x times 5x squared minus 1 over 7x squared. And now we just multiply the numerators together and the denominators together. But of course, when you want to multiply the numerators, it's a binomial times a binomial. So I'm going to bring it up here just to make sure I have some space. So this is 2 times 5x squared, which is 10x squared. Outer is minus 2, inner is plus 5x cubed, and then last is minus x. All of that is divided by the bottom, which is 7x squared times 7x, and that's 7x cubed. So remember, whenever you have a polynomial over a polynomial, we're going to focus on the leading term because that's really determining what the graph looks like. So my leading terms here are right here. So I'm only going to focus on the limit as x approaches infinity, both left and right, positive and negative infinity, of 5x cubed over 7x cubed. And what do you notice happens to the cubes? They are gone. So we're left with a constant, and therefore the limit is just 5 over 7. Okay? Last one. Polynomial over polynomial. This is pretty easy. So we can focus on the leading terms, and that is going to be 5x cubed divided by 4x cubed. I'm sorry, 4x squared. So these are gone. One of these is gone, so you're left with 5x over 4. And so the limit as x approaches infinity, positive infinity of 5x over 4 is actually going to be infinity over divided by 4, which is just positive infinity. But the limit as x approaches negative infinity of 5x over 4 is actually negative infinity over 4, which is negative infinity. So that means that the end behaviors of this graph, as x approaches infinity over here, the graph is going up. But as x approaches infinity in the negative direction, the graph is going down. Okay? All right. Now this is similar to what we just did, okay, but we'll leave one to go over together tomorrow. All right. The next section is revisiting the sandwich theorem. We're finding the end behavior. Now remember, for sine of x, the thing is, if you ask yourself, as x approaches infinity, what happens to the function? Well, it oscillates, goes up and down between 1 and -1, 1 and -1, 1 and -1. So what do we end up using? We end up using the sandwich theorem because of that oscillation of the limit. Basically, I know that any sine function, the limit as x approaches positive or negative infinity of any sine function, so sine of x, sine of 2x, sine of 3x, sine of 10x, over anything, over x, is going to be between less than 1 and greater than, let's ignore the x for just a second, and greater than or equal to -1. Okay, so that's the sandwich theorem. So this works because we are asking about the infinite position, okay? And we can't determine that without understanding that really sine, as it approaches infinity, it really never approaches one specific number. It approaches -1, but then it goes back up to 1, and then it approaches -1, it goes back up to 1. So knowing that, we can use the sandwich theorem. Now this function right here, because it's divided by x, we're going to divide both sides by x. So we find the limit as x approaches infinity of this guy, and -1 over infinity is just 0, and 1 over infinity is just 0. So the end behavior of this is 0. Okay? Now, if we were to look at this graphically, if you were to graph sine of 3x, it also oscillates between -1 and 1. So -1 and 1, you can hold 3x. But the division of 3x does change it a little bit. So that is what needs to be divided on both sides of the oscillation. So now when we figure out the limit as x approaches infinity of -1 over 3x is -1 divided by infinity, again it's 0. And the limit as x approaches infinity of this side is also 0. Now, we can't say -0, okay? So it's -1 over infinity, which is a very small negative number, which is still 0. And this side is 0. So then that means, because these two are equal to each other, that means that the end behavior of this, so the limit as x approaches infinity, both in the positive and negative direction, of sine of 3x over 3x is 0. So do you see the pattern? If you graph sine of 10x on your calculator, you'll get a similar function just like this that oscillates between 1 and -1. But this 10x is what makes the difference. So the oscillation happens between 1 and -1. Okay? But because of this 10x on the bottom, we do have to give it to both sides. And nothing changes. -1 over 10 times infinity is 0. And 1 over 10 times infinity is 0. So the limit of x approaches infinity, both left and right, negative or positive, of sine of 10x over 10x is 0. And we can check this graphically on our calculator, and you will see as you approach the positive and negative, these graphs kind of do something like this. Okay, this is not perfect, but the oscillation gets closer and closer and closer to zero. Okay? So in conclusion, basically, I don't really know what they meant by this box for conclusion, but I just summed up what we just talked about. And the conclusion is the end behavior of sine of x over an x is going to be 0 because using the sandwich theorem, the limit as x approaches positive or negative infinity of sine of x over x is going to be 0. You notice that the infinity, which is a little different than if you approach 0. Okay, this is definitely different, but like we learned in class now, we remember the trig limit. Remember the trig limit for something approaching 0. We use the rule, the limit of something approaching 0 of sine of that something over something is equal to 1. So this one is easy because the somethings are the same. So there's nothing that I need to change on the top, on the bottom. So I know that this is equal to 1. And I'm approaching 0. Now here, we know now from class, in order to, I can't change this 3y, so I need a 3y down here so that I can make this something the same as this. So I'm going to multiply the top and the bottom by 3. And what I'm left with is the limit as y approaches 0 of sine of 3, times sine of 3y over 3y. So now I made my two terms the same. What do I do with this 3? I pull it out. So I'm left with 3, and what is the limit as y approaches 0 of sine of 3y over 3y? It's going to be 1. So this whole thing right here equals 1. So the limit is equal to 3. Okay? Now for this next example, this was not supposed to be there, so let's cancel that out. Okay? And then once we do this problem, I can't change that 5. So how do I make that guy a 5? I can multiply by 5 over 4. But of course, what I do to the bottom, I have to do to the top. So now we're left with limit as x approaches 0 of sine of 5 over 4, sine of 5x over 5x, because the 4's cancel out. 5 times x is 5x. So now the 5/4 comes out. And based on the trig limit rule, as x approaches 0 of the sine of something over that same something is equal to 1. So 5/4 times 1 is 5/4. Okay, so that ends section 2.2, which, you know, was a whole lot of the same, except we focused now more on approaching positive and negative infinity rather than a specific number. All right, good luck, enjoy.